Okay, so we're continuing our discussion about some of the fundamental concepts in graph theory. And so what we're going to be talking about today is different ways of representing graphs using matrices, and also different ways of identifying two graphs or saying that two graphs are the same. And so this has the technical way of talking about this is using something called a graph isomorphism. Right. Okay, and so I want to just begin by talking about how to represent graphs using a matrix. And so the idea is, well, your graph may geometrically look kind of complicated, like you have some collection of vertices and some large number of edges connecting certain vertices to other vertices. And so what's a good way of capturing all the information or storing all the information in this picture? Well, one way to do this is using something called an adjacency matrix. Right. And so how are we going to use a matrix to describe a graph? Right. So maybe let me just draw a particular example quickly. So let's say we have this graph that has 4 vertices. Right, and so I'll have these edges. Right, so this is my graph G. And what we're going to do is we're going to describe G using a matrix that contains only ones and zeros. Okay. And so in fact, we've already seen how to do this in one particular case when we were talking about relations a week or so ago. Remember, if you had a certain relation on a set, there was a directed graph associated to that relation, and we could describe the relation moreover using a matrix of just ones and zeros, where we put a 1 in a certain entry if there's a relation between the corresponding points, right? And so this is going to be very similar. And so what are we going to do? Well, we have 4 vertices. So with the matrix, we'll have 4 rows and 4 columns. And we're going to label each row and each column according to the respective vertices, right? So I'll have a row associated to A, B, C, and D. And then also a column for A, a column for B, a column for C, and a column for D. And what I'm going to do is I'm going to put a 1. Right, so let's first, right, so I'll put a 1 in the entry if there's an edge between the corresponding vertices. Right, so for example, let's just start in the first row, which is the row associated to A. Well, I have an edge between A and A because there's a loop there, so I'm going to put a 1 in that spot. And now let's move on to the next entry in this row. Well, I'm going to put a 1 if there's an edge from A to B. In this case, there is. Moving on, well, there's an edge from A to C, so I'll put a 1 there. And there's also an edge from A to D, and so I'll put a 1 there as well. And so in the first row, what we put all 1s because every single other vertex, including A itself, is connected to A, right? So now let's move on to B. Well, if I look at B, there is an edge from B to A, so I'm going to put a 1 there as well. However, there's no loop at B, so that's a 0, right? Since there's no right. So if there's no edge connecting them, we're going to put a 0. So I'll put a 0. Say 0 otherwise over here. Right. Well, I have an edge connecting B to C, so I'll put a 1 there. If I look at B and D, there's no edge between B and D, so I'm going to put a 0 there. And so on, right? So you do this for every single vertex, right? So I have an edge from C to A, so I'll put a 1, edge from C to B. However, there's no loop at C, and there's no edge from C to D, so I should put 2 zeros there. And then finally for D, well, you can see D is only connected to A, right? So I'll put a 1 for A, and then every other spot has a 0, right? And so this is called the adjacency matrix associated to G, maybe A sub G. Right, and so it's a matrix of 1s and 0s. The rows and columns are labeled according to the vertices. And in each entry in the matrix, you put a 1 if there's an edge between the corresponding vertices, right? Right. And so what is the more rigorous definition of the adjacency matrix? Right. So let's suppose we have an undirected graph G. Right. And let's label the vertices. Well, it's going to have some finite number of vertices. So let's label them V1, V2 up to Vn. Right. So the adjacency matrix is the matrix which has, well, it has n rows and n columns, so we say it's an n by n matrix, whose entry in row number I and column number j, well, the entry in row I and column j is going to be a 1 if there's an edge between the respective vertices, and 0 if there's not an edge. So I'll write this as follows. So aij is going to be 1 if there's an edge between vi and vj, right? So, right, vi is whatever the row you're in, the number of whatever row you're in, and j is the number of whatever column you're in, and this is with respect to whatever order I chose on the vertices initially. And so if there is an edge, you put a 1. If there's no edge, you put a 0. Right, and so this is just more formally writing out what we saw in the last example. Maybe this here is not, this is row. Okay. And so remember, whenever you're working with matrices, right, so it's always row and then column when you're looking at the indices, right? So the rows are the horizontal things and the columns are the vertical things, and this is just a convention, we always do row and then column, right? So always remember that when you're trying to work with the matrix. And so again, why are these important? Well, they're basically, as long as the graph doesn't have an incredibly large number of vertices or a very large number of edges, they're sort of a nice compact way of containing all the information that's important in the graph. What is the important information? It's the number of vertices and also the edge relationships among the vertices. So one thing to point out is that this depends on how I labeled the vertices. Right, so it's possible that if you happen to label the vertices in a different way, maybe your matrix will look a little bit different. It's going to turn out that it's still going to describe the same graph, but maybe the orders of the rows and columns may be a little bit different. And so in fact, there can be many different adjacency matrices associated to the same graph. Right, and so this is related to something we'll be talking about in a few minutes, which are called graph isomorphisms. One thing I do want to point out is that you can also do this for the directed case, right? And so in this case, we just have to modify the definition. So we're only going to put a 1, right? So just saying, when you're looking at a directed graph, if you just say edge, that doesn't make sense, right? Because the edge has to have some direction associated to it. And so we would define it in the same way, but the entry in row I and column j will only be 1 if you have an edge that respects this order, right? So I have an edge from vi to vj, right? Meaning vi is the initial vertex and vj is the terminal vertex for the edge, and then 0 otherwise. Okay. But other than this sort of this obvious modification where you take into account the direction, otherwise it's the same sort of thing. Right. Okay, and so we just briefly mentioned that, okay, well, if I say like I permute the vertices in this description of V, and I change the labels according to this permutation, well then the corresponding entries in row I and column J are going to change because I'm changing the labels of my vertices, and so my matrix is going to look different, right? However, it's still going to be describing the same graph, right? The picture of the graph doesn't change if I just relabel the vertices, right? I have the same image. And so this is related to something called graph isomorphisms, right? And so what are the distinguishing features of a particular graph? So let's say G is given to us as a graph. Right, and so, well, there's two. So the first is just the number of vertices, right? How many vertices are there, right? And then the second is the edge relationships among the vertices. Right, so if I don't show you any pictures and I ask you to say, well, what are the important things on a graph? You're going to say these two things, right? The number of vertices that there are, and then the various connections between these vertices. These are the two main defining features of a graph. And so what is a graph isomorphism? Well, it's some, right, so maybe let me say it this way. So two graphs will be, I'll put it in quotes for now before we define it more rigorously, but two graphs will be isomorphic if these two features are the same, right? So if 1 and 2 are the same. Right, meaning they have the same number of vertices, and also all the edge relationships between the vertices are the same. Right, and so more generally in math, the word isomorphism, which arises in a variety of different subjects, usually means the same as mathematically, meaning certain important features are the same. Right, so I'm putting this in quotes because it doesn't mean they're identical. It just means that sort of if you have some collection of features you're interested in for whatever problem you're working on, for example, the number of vertices and the various edge relationships, that these important features are the same. And so then maybe there are some other unimportant things which aren't the same, which you don't really care about. And those don't matter so much. It can still be isomorphic as long as the important features are the same. Right, and so before I write down the example, let me just look at before I write down the formal definition of the graph isomorphism, let me just look at an example. So let's say I have graph G1, which is just a graph that you get with 4 vertices by completing them into some kind of rectangle or square. Right, so let's say this is my first graph. Well, let me draw a second graph where I'm going to, let's say this is W1, this is W2, this is W3, and this is W4. Right? Well, if I look at these two graphs, they both have the same number of vertices, and they also have the same important edge relationships, right? Because if I basically just, you can get G2 from G1 by just rotating G1 by a certain angle, and then maybe stretching the edges a little bit. But in terms of like mathematically, in terms of the definition of the graph, well, they both have vertex sets with cardinality 4, and every single vertex has degree exactly equal to 2, right? And right, they're both basically the cycle on, right? So they're both basically, I'll put this in quotes, the cycle graph on 4 vertices, right? Okay. You can also imagine modifying G1 to get another graph, which I'll call G3, where I'm going to have, again, 4 vertices. But imagine that the graph G1 is like, it's made of like maybe some string that's connected to other pieces of string at 4 points. And imagine that you flip, say, U2 over U4, You're going to get a picture that looks something sort of like this. Right. And so, right, so imagine lifting V4 off the screen and then putting it above V2 and sort of unraveling this string or something like that. You should be able to go from G3 back to G1 doing that. And if you think about like what are the different edge relationships in this picture G3, if you try to write them down, maybe pause the lecture for a minute and write this down, you'll see that you're basically describing the same thing as G1, even though the picture is a little bit more complicated. And so these three graphs that I drew are going to turn out to be examples of graphs which are isomorphic, meaning all the two important distinguishing features are the same, right? So the edge relationships are the same and they have the same number of vertices, even though geometrically the picture may look a little different. Right, and so what is the definition of a graph isomorphism? Right, so we'll have two graphs. So let G1 and G2 be two graphs. And for now, let's say they're simple graphs, meaning there's no loops. And let's say they're undirected, although you can make this work for directed graphs also. Right. Okay, and so these two graphs are said to be isomorphic, meaning the distinguishing features are the same. If the following condition holds. Well, remember that the vertices have to have the same cardinality, and so in particular, there should be some bijection between the vertices, right? So the first thing we want is, one, there is a bijection, meaning a function f from v1 to v2, right? And so in particular, v1 and v2 have to have the same cardinality. And the second condition we want is that, well, remember that graphs shouldn't be the same just because they have the same number of vertices, right? We want to preserve the edge relationships. And so we want this bijection to have a special property, right? And so what is the property? So if there's an edge between A and B, where say A and B are two vertices in V1, then, well, f of A is some vertex in G2, and f of B is some vertex sorry, f of A and f of B is also some vertex in G2. And so we want the edge relationships to be preserved. So there should be an edge between f of A and f of B, right? Right. So we want there to be, then there is an edge between f of A and f of B. Right, so this function, if I go back to what I wrote less formally on the last page, right, so this function is a function this function f, it preserves these important features, right? It preserves the number of vertices, and it also preserves the edge relationships among the vertices. Right, and more formally, the way to say this is that it's a bijection such that whenever there's an edge between A and B, there's also an edge between f of A and f of B. Right. So if I can find such a function, then my graphs are said to be isomorphic because these two important features are the same, right? And so let's look at the previous example, the more complicated part of the previous example. So we had the first graph was basically C4, or the cycle on 4 elements or 4 vertices, right? And so this was my G1, and then let's call, I'm going to relabel instead, say G2 instead of G3, and that'll be this vertex that we got by kind of informally imagining like flipping over part of the graph. And so the claim is that these are isomorphic. Right. And so how are we going to show that they're isomorphic? Well, we have to find a function that satisfies these two properties. And so, well, there's only four vertices, so let's just try to like brute force find the function by hand. Right, so I'm going to define f as follows. Well, let me just say f of u1 is equal to v1. Why not? Right. Well, if I say f of u1 is equal to v1, notice that v1 is connected to v4. So whatever I choose to send to v4, it has to be connected to u1 by an edge, or else property 2 would fail. Right. So for example, well, u1 is connected to u2, so maybe let me say let f of u2 equal v4. Right. So notice that if I sent f of u2 equals v2, that wouldn't work, right? So let me put that as a warning. Right, why won't this work? Because there's no edge between v1 and v2, right? So if I define my function this way, then property 2 will fail, meaning it's changing the edge relationships are not preserved, and therefore this would not be the kind of function that we're after. But f of u2 equals v4 is a good choice. And then, okay, well, now let me move on to f of u3. Notice that f of u3 is connected to u1. So whatever notice that u3 is connected to u1 by an edge. So whatever I choose for f of u3, it better be connected to v1 by an edge. And so, for example, we can say f of u3 is equal to v3. And then finally, we have to define the function on u4. Well, there's only one choice left, so we have to say f of u4 is equal to v2, right? And so you can check that well, this function is definitely a bijection because I've just, right? There's not two values that are going to the same place, so it's injective and it's clearly onto, so it's a bijection. And so the important thing to double check is just property 2. That whenever I have an edge, if I look at the image or the corresponding points that this function sends the two vertices to, that there's still an edge between those, which you can check for this example. Okay, and so, right, that's hopefully not too complicated of an example. There's still a more general problem which is raised by the previous definition, which is, well, if I'm given just two graphs, how am I going to determine if they're isomorphic beyond just the brute force guess and check that I was trying on the previous example? And so, unfortunately, in general, this is a very hard problem, which is still not very well understood. Right, and so, for example, there's a major open problem in I guess, the intersection of math and computer science, which is finding an algorithm that takes two graphs as the input and checks whether or not they're isomorphic in polynomial time. Meaning if the vertices have size n, you want your algorithm to be big O of n to some power. And so finding such an algorithm is still an open problem. It's related to this more complicated problem of the relationship between P and NP, if you know anything about more advanced complexity theory. So there's recently actually been some progress on this problem. So about 5 years ago, an algorithm was discovered that does solve this problem in something called quasi-polynomial time, which is somewhere between polynomial and exponential. But if you want to understand this, or if you want to find an algorithm in polynomial time, this still seems hard and out of reach, right? And so the short summary is that there's not really any known fast way to check if two graphs are isomorphic if they have relatively large size. However, there are a variety of techniques you can use if the graphs are small to sort of immediately check if they're not isomorphic, which I'll talk about now, right? So it's easier in some cases to see that graphs are not isomorphic, although this depends on sort of an ad hoc thing. It depends on the particular graphs you're given. Right, and so what are some examples? Right, so let's look at these two graphs, G1, which I'll draw. And G2. Right, and so, well, if I asked you to determine whether or not these two graphs are isomorphic, there's actually a very, very easy way to do this, just because, well, notice that G1 has 4 vertices and G2 has 5 vertices, right? And so they can't be isomorphic. Right, because you can't have a bijection between a set of cardinality 4 and a set of cardinality 5. And so you can just see by inspection, by comparing the number of vertices, that two graphs are isomorphic, right? So they need to have the same number of vertices. Right, so let's look at another example. So, right, so in this case, I will have two graphs with the same number of vertices. Right, so let's say G1 is this graph. Let's see. Sorry, I have to very carefully check my notes when I draw these, or else the example could be wrong. Right. So let's say G1 is this graph and G2 is this graph. Right, so it looks sort of similar, but maybe there's a vertex sitting up here alone. Well, these can't be isomorphic. Well, why can't they be isomorphic? Well, if I look at G2, notice that there's an isolated vertex, but there's no isolated vertex in G1. Right. Right, so, right, what is the isolated vertex? It's just this. So there's no edges connecting to this. Right, so let's suppose we had an isomorphism from G1 to G2, then I would need some function from the vertices of G1 to G2. But on the other hand, well, remember that for any bijection, you can always look at the inverse. So it's the same as assuming that there would be a bijection from G2 to G1 that preserves the edge relationships. But if let me call the isolated vertex in G2 A. So let's suppose I had this function. Well, what am I going to send f of a to, right? So if I send f of a to any one of these vertices, well, then every single possible choice for f of a has some edge connecting to it. And therefore, if I go back to G2, in order for my function to preserve the edge relationships, there would have had to be some other edge connecting to A, but there isn't, right? And so therefore, these two graphs cannot be isomorphic, right? And so another way of saying this is that, well, this vertex A and G has degree 0, but there's no vertices of degree 0 in G. In G1, right? And so this is let me characterize this as a theorem. And so two graphs, G1 and G2, right. Let's suppose. So let's suppose that G1 and G2 are isomorphic with the function f, the bijection from V1 to V2, which is the bijection that you need for them to be isomorphic. Well, the theorem is that for any V in V1, if I look at the degree of f of V, that has to equal the degree of V, right? So this is the degree in G2, right? So say f is going from V1 to V2, the degree of f of V has to equal the degree of V in G1, right? And so the previous example we looked at, this fails because A has degree 0, so, but no matter where I send A for any function from G2 to G1, there's no vertices of degree 0, right? Right, and so how do you prove this? Well, this is just a direct consequence of the fact that that the function f preserves the edge relationships, right? So imagine if, let's say V, right? So let me get some more space on the next slide. So what is the proof? Well, suppose V is connected to let's say W1, W2 up to WR, right? And so the degree, let's say these are in G1, and so the degree of V is equal to R, right? So these are other vertices that are connected to V by an edge. Well, then f of V is connected to exactly, well, f of W1, right? Because I need to preserve these connections with my function, f of W2, and so on up to f of WR. So this shows that the degree of f of V is at least R, right? Because I have R distinct vertices in G2 in the second graph. Well, how do you know that the degree of f is less than or equal to R, or is exactly equal to R? Well, if there happened to be an additional vertex that f of V was connected to, right? So let's say this is f of V, and let's say there was some WR plus 1, right? Some other vertex. Well, WR plus 1, this has to equal f of U for some U in the original graph, because, well, my function is a bijection, and so therefore V would have had to be connected to U, right? So we would need V connected to U, and so therefore this would have been in the original list, right? Right, let me write it like this, right? So U would have been in the original list, right? So this shows that the degree is actually exactly equal to R, which is the degree of V, right? And so one easy way to check if two graphs are not isomorphic is to just compare the degrees of the vertices, right? So let's do one more example of this. And so in this case, my graph G1 will look like this. And my graph G2 will be very similar, with one important change. So I'm going to have an additional edge connecting here. Well, if I look at this graph, this vertex here has degree 1, right? But if I look at G2, there's no vertices in G2 of degree 1, right? And so therefore, if I had any isomorphism or any function f with the two properties, there's nowhere to send this vertex with degree 1, because there would have to be another vertex in G2 with degree 1, but there aren't, right? So these are not isomorphic. Right. Okay, so those examples at least show that in certain cases, if there are these sort of fundamental properties of the graph are different, like there's vertices of different degree or the cardinality of the vertices are different, then the graphs can't be isomorphic. And so you always want to look for, if you're trying to detect if two graphs are isomorphic, you want to check for these things first. So the harder problem though is, well, what if two graphs actually are isomorphic? Like what if you can't rule out an isomorphism because of these reasons? How do you actually check if they are? Like how do you actually find the function? And so this brings us back to this problem, which is very hard of determining if two graphs actually are isomorphic. And so let's just do one more example like this, where it turns out that they actually are isomorphic, and we'll check it using the brute force guess and check technique. Right. So what we're going to do is show that the following graphs are isomorphic. Right. And so my first graph is going to be G1. Oh, sorry. Right, so I'll have these edges. Right, so this is G1, and then G2 will be the following graph. Right, so say U1. Right. So this is G1 and this is G2. And so what we want to do is show that they're isomorphic. And so we'll notice that the vertices have the number of vertices in each graph is the same, right? So they both have 5 vertices. And moreover, there's no obvious reason that they're not isomorphic, like in the previous example. Like for example, there's no isolated vertex in G1, and right, there's no isolated vertex in G1, but G2 doesn't have any isolated vertices, or there's no obvious disparity in the degrees of the vertices. And so after you check these things, you may think, okay, well maybe they are isomorphic. So how do you actually show this? And so what we're going to do is just again use the brute force method. So we're not going to just completely randomly guess, right? There's still some general principles you can use to guide you. But otherwise, we're just going to try to find f by guessing. Right. And so we're going to begin by, well, let's just begin with, let's say, v3. Right. So what am I going to send f of v3 to? Well, so notice that v3 has degree 3. Right. So if I look at the picture, v3 is connected to v1, v2, and v5. And so whatever this is, I need to make sure that f of v3 has degree 3 because of the theorem we talked about previously. Right? So let me just pick one of the vertices in G2 that have degree 3. Right? So for example, let me pick U5. Right? So let's say f of v3 is equal to U5. Okay, and now the next thing to do is, right, so there's no inherent problem with this choice, but we've only picked one value of the function. And so the next thing to do is move on to other vertices in G1. To be smart about this, though, we want to make sure that we're not disrupting any of the edge relationships with V3. So I should move on to other things that are connected to V3, right? So for example, let me move on to V2, right? Okay, so what is this going to be? Well, there's two things to point out. The first is that, well, V2 has degree 3. So f of v2 needs degree 3. Right. because this function has to preserve the degree of the vertex. Actually, we know a little bit more because notice that also, well, there's an edge between v2 and v3. And therefore, since this function has to preserve the edge relationships, whatever I assign f of v2, this has to be connected to f of v1, or sorry, f of v3, right? And so in particular, I need to pick something for f of v2 that is connected to u5, right? Because u5 is equal to f of v3, right? And so, right, so what I need to look for, a vertex with two properties, it needs to have degree 3, and it needs to be connected to u5. Well, if we look at the graph, well, what's connected to u5? I have u2 is connected to u5, and u3 is connected to u5, and u4 is connected to u5. But among those, there's only one that has degree 3, right? And in particular, u4 is the only vertex connected to u5 that has degree 3, and so we have to pick u4, right? So assuming the choice for f of v3, that forces us to pick u4 for f of v2. Right. So even though we're kind of guessing and checking, at each step every single guess that you make is going to determine what you have to do for the next few choices, generally speaking, right? So the first few steps influence the steps that come after, because you have to maintain the edge relationships, right? Okay, and finally, let's continue along. So let's now move on to v1. Right, so now notice that v1 has degree 2, and so I want to pick something that has degree 2. However, I also need to make sure that, well, notice that v1 is connected to v2, and so whatever I choose for f of v1, it needs to be connected to u4, right, because it needs to be connected to f of v2. Although there's a little bit more, so let me sort of, instead of just saying this, let me write it down as well. So, well, v1 is connected to v2 and v3, which we've already assigned values, or to which we've already assigned values. And so whatever I pick for f of v1, it has to be connected to u5 and u4. And it also has to have degree 2. Right, so what are the vertices that are connected to both u5 and u4? Well, I have u2, and that's it, right? So in fact, there's only one vertex that's connected to both u4 and u5, so therefore f of v1 is actually also determined, so it has to be u2, right? So right, so notice that the initial choice I made for f of v3 actually forced me to pick f of v2 to be u4, and then those together forced me to pick f of v1 to be u2. Okay, and finally, we have to assign values to v4 and v5. Right, and so continuing along this process, at this point, there's only a few things you can really do, right? Because we only have now 2 values for v4, and the choices we've made are already going to very strongly restrict what we can do. Right, so in particular, well, v4 is connected to v2, so that means f of v4 has to be connected to u4, and so f of v4 can be either u1, u2, or u5, but u2 and u5 are already taken, right? Remember, we need this function to be a bijection, so this has to be u1. And then finally, well, now that we know f of v4, v1 and v2 and v3, there's only one choice left for f of v5, so the only thing left is u3. And so after going through this kind of complicated process of guessing and then checking everything that is consistent with your guess and then moving one step at a time. We've exhausted all the vertices, so we're done. And so this is a candidate for our function. And now you just have to go back and double check. Well, it's clear that this function is a bijection. You just want to double check that all the edge relationships are preserved, which you can do, and you can see that this is indeed an isomorphism between the two graphs. Great. Right. So one way to actually make this process easier is to actually go back and use the adjacency matrices, which we introduced at the beginning of the lecture. Right. So that what's the helpful way to check that F from the previous example is an isomorphism? Well, the main thing we need to check is that it preserves the edge relationships. Right, and so one way to do this is to just draw down the adjacency matrices. Right, so what I'm first going to do is just quickly copy down the adjacency matrix for G1, which you can check. Right, so if you go back and maybe copy the graph from the last page, you can double check this as I write this. So I have right, so this is the adjacency matrix for the first graph. And so what I'm going to do is now form the adjacency matrix, not necessarily for G2. What I'm going to do is do an adjacency matrix for, like, I'll put this in quotes, for F of G1, like where the function assigns or sends the respective vertices. Right, so in row 1, I'm not going to have U1 in row 1, but I'll have F of V1, right? Whatever F happens to send V1 to, and then I'll have F of V2, F of V3, F of V4, and F of V5. And similarly, I'll order my columns according to where the function sends the order from G1. Right, and so, right, so well, what was F of V1? Remember, this was U2. F of V2 was U4. F of V3 was U5. F of V4 was U1, and F of V5 was U3. Right, so this was U2, U4, U5, U1, U3. Right, and so now if I look at the original graph G2, and I draw the corresponding edge relationships with respect to this order on the vertices U1 through U5, well, you'll see that you get the same matrix, right? Right, so you can check that the matrix is going to be the same. Right, well, right, so why is this the case? Let me just copy this picture over, and right, so. Right. So this is my G2, and you can check that everything all the ones and zeros here I put are in the proper places, right? So there's no vertex, there's no edge between U2 and itself. There's an edge between U2 and U4. There's an edge between U2 and U5, and so on. Right. And so if you do this in this way and you get the same matrix, well, you can see comparing these two that you have the same matrix. That means that all the edge relationships are the same, and therefore this function has to preserve the edge relationships, so it has to be an isomorphism. And so this was maybe a little bit long-winded as a maybe a long-winded comment adding on to the previous example. But the main point is that, let's say you do the process that we did for this example to guess for a particular choice for your function f, like we did here, where I picked 5 values for my function. Well, sometimes it's going to be very complicated to actually double check all the possibilities to make sure that you got the right answer. And so one more compact and easier way to do this is to, well, just draw the adjacency matrix for G1, and then draw the adjacency matrix for f of G1 in the way that I did it here, where you're changing the way you label things according to where the function sends v1, v2, v3, and so on. And then if these two matrices are the same, then the function has to preserve the edge relationships, and so it has to be an isomorphism. All right, and so that's it for today. So we'll pick up next time. So next time we're going to be talking about paths through graphs and connectedness of graphs and things like this.